In this video, we're going to be looking at graphs. In this particular slide that we're looking at now, it is a distance versus time graph, or we could say it is a position versus time graph. That's another way to think of it. We are ranking these on this slide based on velocity. And we know that velocity is equal to displacement over time. Velocity is a vector, displacement's a vector. And so if we look at A, and we look at the slope, slope is equal to rise over run. And so in case A has a relatively small slope or a relatively small rise over run. Now the rise is the change in the position, which can be given the symbol x. So that's delta x over the run, delta t. So the slope here is equal to delta x over delta t, and that is the velocity of A. So it has a small slope, and therefore it has a small velocity. If we were to look at, say, case C, and if we were to try to do about the same run, we see the rise is much more. So the delta x is definitely bigger. Delta t, I picked it to be about the same as the one down here. So this one has a bigger slope. And you can just see that as you go from A to B to C all the way up to F, the slope increases. And so F is the one going the fastest, and A is the one going the slowest. So those are quite easy. And so in your explain the reasoning, you can say since the slope of a position versus time graph, don't need a comma there, is equal to the velocity, we can rank them by slope. All right, let's look at the next one. Here we've got a velocity versus time graph. So you got to pay attention. The axes changed, and we're also changing what we're ranking them on. We're ranking them on acceleration. Oh, and it has a 1 there, so I'll just write this out here. Acceleration is equal to delta v over delta t. Velocity and acceleration are both vectors. And so we look here, we look at the rise over run. So the rise here is going to be delta v, the change in v, over delta t, change in time. And so here we can rank these similarly. Say since the slope of a velocity versus time graph is equal to the acceleration, we can rank these by slope. And so therefore A has the least slope, then B, then C, then D, then E, and then F. Okay. How many of these are moving at a constant velocity? It doesn't ask you that, but I'm asking you now. What do you think? How many of these are moving at a constant velocity? If you said none, you're correct. Okay? Think about it. We could put a scale on here. Let's say that's 1, 2, 3, etc. Well, the velocity at the beginning for A, object A, is moving at 0 meters per second. Later on, it's moving at about a ½ meter per second, then 1 meter per second, 1.5 meters per second. So no, that's not a constant velocity. It does, however, have a constant acceleration. Okay, so it has a changing velocity, but constant acceleration. All right, and that's true for all of them. They all have constant accelerations, but each one has a different constant acceleration. And we're going to be taking advantage of objects that have constant acceleration because we have a set of equations that you're going to see in the next module called the kinematic equations of motion, and you're going to use those to predict and to determine, calculate various unknowns in a lot of situations, but they're only going to work when the acceleration is constant. Doesn't mean the velocity has to be constant, only the acceleration. All right, let's take a look at one more graph. Here we're also ranking them for acceleration. If we look back to the last one, we were ranking those on acceleration, and this looks like the same graph. However, the axes are different. Well, just the vertical one. The velocity is on the axis, the vertical axis here, but on this one, it's distance or position. So we're asked about acceleration, and we remember that acceleration is equal to delta v over delta t. So it's a little bit more challenging here. We're not given a velocity versus time graph, but we're asked to rank their acceleration. So can we figure anything out about acceleration here? Well, let's just look at case A. Case A is moving along, and it has a certain slope here, and it has a certain slope later on. Well, the slope stays the same. Okay, for A, the slope is constant. And on a position versus time graph, the slope is equal to the velocity. So we can therefore determine that the velocity is constant. And if the velocity is constant, then we know what about the acceleration? That's right, the acceleration is equal to 0. And then we go to case B, and we see that for B, the slope is constant. And if the slope of B is constant, then the velocity for case B is constant. And if the velocity is constant, then we know the acceleration is constant. I'm sorry, I said the wrong thing. The acceleration is 0. The acceleration is also constant, but more importantly, it's 0. And those things get mixed up. And so I'm glad that I made that mistake there so I can point it out. Saying that the acceleration is 0 is not the same as saying the acceleration is constant. Okay, if you think about, there's lots of things where we could have constant acceleration, but the acceleration is not 0. So we could have something speeding up with a constant acceleration. Or we could have something like this, where it has a constant acceleration of 0, and it's not speeding up at all. Remember, this is a distance versus time graph. And so this thing is getting further and further away, but at a constant rate. And so the acceleration is 0. So they're all going to have an acceleration of 0. And so A, B, C, D, E, F. It's a tie. So let's see if we could explain that, get some words to go with that. Say, since slope is constant on each x versus t graph, velocity is constant for each one, and that means acceleration is equal to 0 for all of them. So that's why it's a tie.